All right, so now we move on to lesson 4.3, and that's solving quadratic equations by completing the square. So we've introduced the first algebraic method in a previous lesson, which was factoring to solve for x-intercepts, roots, or zeros. But now what we're going to talk about is our second method, which is completing the square. Now we did a bunch of completing the square in unit 1, which was quadratic functions. Now we're just going to take that exact same skill and then complete the square in order to solve for specific x values. And this is what we're eventually going to call the square root principle, or taking the completed square method and then expanding that one step further and using the square root principle to figure out what these specific x-intercepts are, or the x values that make up the root solutions or zeros. All right, let's do a bit of review here. So suppose that we have a perfect square trinomial such that we have in the box here, x squared plus 2xy plus y squared. Well, this was always equal to an x plus y or an x minus y squared, where the middle sign, or this middle value here, the plus minus, whatever is in this position determines the sign that goes in the binomial. So what I'm going to quickly write here is that this, either being positive or negative, determines the sign. So if it ends up being positive, that will be a positive in the binomial. And then if it's negative in the factor, or negative for the b term, it's going to be negative in the binomial. Now let's take a look at this in a bunch of perfect square trinomial examples. So example 1, we look at this one, and if you're unfamiliar with this one, let's just throw a 1 in front of x squared. That's going to make this the following. The square root of 1 is equal to, we actually are going to put in 1x as well, because we want to make sure that that goes in there. This is going to give us 1x. Then I'm going to do the square root of 25. Square root of 25 is equal to 5. Therefore, my factored form is going to be x and then 5. But then we're like, how do we know the sign that goes in the middle here? Remember, it always comes from the b value, as mentioned just before. So it's going to be x minus 5 squared is our solution to this. Okay, we're going to go to our next example. We're going to take the square root of 4x squared, which is equal to 2x. We're going to take the square root of 9, which is our other outside term, which is 3. Therefore, our factored form is going to be 2x and 3. And then we're like, what is our middle term here, or our middle sign on this? It's going to come from the negative in the b. We're going to throw a negative here. All right. Now for our last example, don't be thrown off by the multiple variables. We're just going to include them both. This is going to be 25x squared y squared, which when we take the square root of this is 5xy. All terms get square rooted. Now I'm going to square root 1, which is equal to 1. Therefore, my factored form is going to be 5xy. And then we're going to leave a gap and put 1 squared. How do I know if it's positive or negative? I always look to the middle term and I say that it's a positive. So therefore, this is a positive. Awesome. Okay, so there's our terms for all three. And what we'll do is we'll zoom out, just highlight them all just to make sure that we save our solutions. There's the first, there's the second, there's the third. All right, the reason I went quite quickly through that is because that's a review of our first unit, which was all about factoring the different methods, and this occurs in Math 10C. Now, let's make a special note as we move forward here. Before we actually go into using the square root principle, we need to be aware of what it is. So when we take the square root of some sort of equation, on the opposite side, when we take the square root, whatever that number is, we need to make sure that it is the plus minus version of that. So suppose we have this off to the side. Prime example, x squared equals 4. If I square root both sides like this, square root and square root, well, when I square root 4, we know the square root of 4 is 2, but by square root principle, it's actually positive and negative 2. We would say that this is equal to plus minus 2. And that's sometimes the way we write the plus minus being like this on top of each other as a vertical stack. It means that it's either the positive or negative solution. And then we could write them individually and make it 2 and negative 2. But we need to be aware that anytime we take a square root in quadratic equations, we always need to make sure we're taking the positive and negative case. And this will make sure that we're looking at this in the appropriate way of there being potentially 2 solutions. And again, this is called the square root principle. Okay, let's go down below. Example 2. We're going to solve the following quadratic equations using the square root principle. Now, some of these may be more simple than others. Some of them might require more work than others. We're going to do as much algebra as we need to in order to get them to simplified exact values. When they say simplified exact values, that means we do not want decimals. If we wanted a decimal, they'd be very specific and say like, give it to me to the nearest tenth or nearest hundredth or thousandth. But in this case, when they say exact values, which is very common at the 30 level and diplomas, that means that we want to keep it as some sort of radical or some sort of whole number. Okay, now let's take a look at a. With a, if we want to isolate for this a value, we're going to divide both sides by 3. When we divide both sides by 3, this is going to give us a squared is equal to 64. Now what we need to do is take the square root of both sides, and then similar to the example above when it was x squared equals 4, this becomes a is equal to plus minus 8, and therefore that's our solution. We could separate it, we could write it as a equals 8, a equals negative 8, but I'm fine keeping it as a combined solution. All right, let's go on to B here. We look at this one. Well, is there anything we can move across or divide? No. So there's no coefficients to divide. There's nothing to like get rid of. The only step here we can do is now square root both sides. I square root the x minus 5 all squared, square root 0. This gives me x minus 5 is equal to plus or minus 0. Putting plus or minus 0 is a little ridiculous because we know there's no such thing as going to the left or right of 0 in terms of actually being at 0. So it's not going to have a positive or negative value. That means the only solution that is possible here is x minus 5 is equal to 0. If we add 5 to both sides, so we're going to go plus 5 and plus 5, this is going to give us one solution of x equals 5. Now, more on this later because we're actually going to state what this actually means graphically or even just visually generally. We need to be aware that this, when we, instead of getting one value, we only get, or instead of two values, we get one value. This actually has something different in terms of meaning. Okay, let's go over to example C. On example C, it's getting a little more complex. We're blending a bunch of the topics together. I'm going to add 49 to both sides. When I add 49 to both sides, it isolates the squared term. So 2x plus 5 all squared is equal to 49. This is what we want. We want that squared term, whether it's a binomial or monomial or even trinomial, we want to make sure it is on its own. We're then going to square root both sides. If I square root both sides, this is going to give me the following. 2x plus 5 is equal to plus minus 7, because anytime we take a square root, we must plus minus. Now what I'm going to do is separate it into the following two cases. 2x plus 5 is equal to positive 7. My other case is 2x plus 5 is equal to negative 7. Now, in isolating this, we're going to subtract 5 from both sides, and we're actually going to do that on both of these equations. When we separate them in the following way, we're going to get 2x is equal to positive 2, 2x is equal to negative 12, and now what we're going to do is divide both sides by 2 in order to isolate our x on both of these equations, and therefore we're going to get x is equal to positive 1, x is equal to negative 6, and there's our two solutions. So instead of the one solution that we got on the previous one, or the two solutions that we got in part A, we're again getting the part, this part, there's going to be two solutions. All right, let's move down to D here. So we're going to scroll down to the following example. If there's a coefficient in front of the squared term, always be looking to divide that away. Now, if there's some other term here being added or subtracted, I would move that before you do the division. I mean, you could do it before, but it might be helpful to do that. In the case of this one, there's no number being added or subtracted, just this number out front. So I'm going to divide both sides by that number. Divide by negative 3, divide by negative 3. And when you divide by negative 3, we're going to get x plus 3 all squared is equal to negative 41. I'm going to square root both sides as follows, because we always want to make sure we're square rooting as to get rid of the square that is on the x plus 3 binomial. This gives us x plus 3 is equal to the square root of negative 41. And then you should be thinking, oh no, this is not good. Circle this, put a line through it. This cannot work. This is actually not a real number. If you square root a negative, it's a non-real number. So therefore, if this is a non-real number, which we're going to classify it as that, non-real number, because eventually what you'll say is these are actually imaginary numbers, but I mean, that's not till in university or the post-secondary level, if you even decide to take math that far. So we don't want to get super complicated with these things. It's a non-real number. We cannot do this at our level. So therefore, if it's non-real, there is no solution. Or we could say even no real solution. That would be another way to phrase that. So please watch out for those negative square roots. The negative square roots are not possible for us at this level until we introduce the complex plane, which for many of you, you might actually never see. All right, we're going over to E. In this case, E, there's some fractions here, but just like before, what we're going to have to do is add our term across or subtract it if it was being minus or added. But in this case, because it's being subtracted, we're going to go plus 1 over 8. This is going to give us 2x plus 1 over 2 all raised to the power of 2 is equal to 1 over 8. Now what we want to do is divide by that 2, because remember, we don't have that coefficient out front of these brackets. Before you square root, please take care of this. If there is a number out front of the bracket, more specifically in the coefficient spot of the squared term like this, divide it away. It must be eliminated. Now, when we eliminate it from the left-hand side, this leaves us with x plus 1 over 2 all squared. And then on the other side, 1 divided by 8 divided by 2, or 1 over 8 divided by 2, is the same as 1 over 16. The 2 and the 8 multiply together. And if you don't believe me, type it into the calculator or show it algebraically using the flip rule. Now from here, what we're going to do is take the square root of both sides. I take the square root of the left, square root of the right. This leaves me with x plus 1/2 is equal to, the square root of 1 is 1. The square root of 16 is 4. Therefore, this is my opposite side, but I'm missing something. Before I place that in there, make sure I put a positive and a negative, or a plus minus 1/4, because if I take the square root, I must have the positive and the negative case. Now what we're going to do is just separate these into their own sections here. So this is going to be x plus 1/2 is equal to the positive 1/4, and then on the other one, it's going to be x plus 1/2 is equal to negative 1 over 4. Now from both sides, we're going to subtract away 1/2. So subtract 1/2, subtract 1/2, subtract 1/2, and let's just make sure I get that actually as a 1/2 minus 1/2. On the left-hand side, this is going to be x is equal to 1/4 minus 1/2. This is the same as saying I'm going to get negative 1 over 2, and I can't reduce that anymore, so there's the solution. On my right-hand equation, it's going to be x is equal to negative 1/4 minus 1/2. This is the same as saying negative 0.25 minus 0.5. That's negative 3 over 4 as a fraction. There we go. There's our values, or there's our solutions to this equation. Okay, now let's flip forward here. Example 3, solving quadratic equations by completing the square. So in this example, what we're going to need to do is take this trinomial, write it in vertex form by using the algebraic method of completing the square, and solve for x. So pretty popular way you're going to see these, and what they might do in some of these equations is have like 2 of the terms over on the other side and then leave the x squared here, or have the x here and then put these 2 terms on the other side. What you want to do is bring them all to the same side and set it equal to 0. Now, let's complete the square with this example here. So what we're going to do, first and foremost, we want to look for a GCF. Is there a GCF of 3, 12, and 5? No. So we're not going to divide this original equation by anything. Second part, I want to pair together my first 2 terms. Negative 3x squared minus 12x in brackets, and leave the constant term outside of the brackets as such. Now, when we do this, here's what we're going to have is we need to remove out the GCF, which in this case is 3 from the brackets, leaving us with x squared plus 4x plus 5 on the outside is equal to 0. So we've paired together the first 2 like we always need to do, make sure brackets go around them, divide both by what's possible, leaving the x's behind because we don't want to deal with the x's, keep them in the brackets. Now what we're going to do is we're going to do our b divided by 2 method. B divided by 2 squared is equal to 4 divided by 2 squared, which is equal to 2 squared, which is then equal to 4. Now, in class, in that first unit, or I should say in quadratic functions, we highlighted that b divided by 2 every single time because we knew it appeared in the final solution, or that final vertex form. So please highlight it there. Now, let's make a substitution here. 3x squared plus 4x. We're going to add 4, which was the squared term, minus 4, which is a plus minus of the same term, and then we're going to keep that 5 on the outside equal to 0. I'm then going to remove this 4 out. I don't want to deal with this 4. This 4, let's get rid of it. Pull it outside of the brackets. We must multiply the negative 4 by the, not the exponent, but the coefficient negative 3, because if that 3 is connected to it, in order to remove this out, we must multiply it by the leading term. So this is going to become negative 3 x squared plus 4x plus 4. We're going to leave the positive 1. We're going to remove that negative 4, but we must multiply it by the negative 3 out front. Plus 5 is equal to 0. We're then going to rewrite this as 3. Instead of the trinomial that we see on the inside here, we know that the term that makes up the binomial comes from our b divided by 2. It's x plus 2 all squared. Negative 4 times negative 3 is 12. 12 plus 5, this is going to be equal to 17 on the outside. So we're going to write it as positive 17 is equal to 0. Awesome. Now from here, we want to subtract away the 17 from both sides because we want to isolate that squared term. That's our whole goal. So we've made this into vertex form, which is technically this piece above. Now we're going to start doing the algebra to solve for x. When I subtract away 17, it leaves me with 3x plus 2 all squared is equal to negative 17 on the other side. Once we get here, we must divide both sides by the 3. We're going to do that up above on the right-hand side here. So we have that term of negative 3x plus 2 squared equals negative 17. I'm going to rewrite this up here. So negative 3x plus 2 all squared is equal to negative 17. We're going to divide both sides by that coefficient. There we go. When I divide, it's going to give me x plus 2 all in brackets squared is equal to positive 17 over 3. Because remember, if we divide both sides by the negative, we need to make sure that that shows up as now a positive. Negative over negative is a positive. Now we're going to take the square root of both sides, square root and square root. Now this is going to give us x plus 2 is equal to plus or minus the square root of 17 over 3. Now you're probably thinking, why did we not get rid of the radical? Well, square root of 3 is irrational. Square root of 17 is irrational. They're actually both prime numbers, so we don't want to get rid of it. Now what we're going to do is we're going to simplify this into the following manner. There is two cases. X plus 2 is equal to the positive square root of 17 over 3. And the other case is x plus 2 is equal to the negative square root of 17 over 3. Now, what this leaves us with is the following solutions. We're going to get x is equal to negative 2 when we subtract it over, plus the square root of 17 over 3. And the other case is going to be x is equal to negative 2 minus the square root of 17 over 3. There we go. And here is our two answers in simplified exact form. Remember, unless they say we want a specific decimal, which in this problem, let's just zoom out and make sure, yeah, they didn't ask for a specific x value in terms of like a decimal to the 10th or the 100th or the 1000th. When there's no specification, I would leave it as the radical or leave it in the most whole number form possible, because we want to look at these things from an exact value point of view, and that's going to be more important to us. All right, so we've seen one example of how that completing the square technique from our Unit 1 quadratic functions is now coming back to help us out in solving for specific x values in the equations. Now, let's do the same thing for example 4, just with a bunch of new examples. Complete the square, express all answers in simplified exact values. Again, simplified exact values we know are non-decimal solutions, and you're going to see that a ton moving forward, including in the trig unit and radical unit and all this other good stuff. So let's just make sure we hold on to that idea of what an exact value is. Now, we're going to walk through these quite quickly just because they will tend to be a bit of a review. You'll probably look at these on surface value and be like, oh, we've seen these all before in a very similar manner. So in terms of the methodologies, so don't be super thrown off by it. If you need help with these things and you need to watch it a couple times, for sure do that and try and practice these things out as much as you can on your own. Okay, first one, we're going to take this and we're going to group our first two terms. It's going to be x squared plus 12x bracket minus 8 is equal to 0. There's no greatest common factor, so we go right to our b divided by 2. b divided by 2 squared, this is 12 divided by 2 all squared, which is equal to 6 squared, which is equal to 36. Now we're going to go x squared plus 12x plus 36 minus 36 on the outside minus 8 is equal to 0. Now from here we're going to rewrite this as x squared plus 12x and then keep the positive 36 in the brackets. I don't want to leave that out. Minus 36 minus 8 is equal to 0. Now, I'm going to pause here just for a second. Some of you might be like, wait a minute, we removed this out and we didn't multiply it by some coefficient, but I mean, technically we did. Negative 36 times positive 1, which is out here, just leaves us with the same term. So I just wanted to make sure we point that out. The second thing I want to point out is our b divided by 2, which is 6. Let's make sure we square or we highlight this or box it because we know it's going to come up in our next step. So instead of this trinomial, I'm going to write it as x plus 6 all squared. And then it's going to be negative 36 minus 8 is going to be equal to negative 44, which is equal to 0. Now what I'm going to do is I'm going to add this to both sides. So I'm going to go plus 44 and plus 44. When I add 44 to both sides, it's x plus 6 all squared is equal to 44. I'm going to square root both sides to eliminate the squared term. This is going to give me x plus 6 is equal to the square root of 44. Now, the square root of 44 can actually be reduced. In fact, And I'm going to take this step further. Because we are going to keep it in a radical form, the square root of 44 doesn't actually give us an exact square root. We're going to write it as plus minus the square root of 44. In our steps of actually separating these into the two different x's, I want us to write it in the simplified form for this. Now, to write that, over here, what is the largest perfect square that divides 44? It's actually 4. That means that we could rewrite the radical like this, and I'm going to just do it in a two-step, plus or minus the 4 times 11, which is also equal to plus or minus 2 root 11. We always want to reduce our radicals. And so in this case, it's x plus 6 is equal to plus or minus 2 root 11 in the reduced radical form, which we'll get more to in our radicals unit, but this is an expectation that you're going to be reducing these radicals. Now, in the two different cases, it's x plus 6 is equal to plus, and I don't even need the plus there, 2 root 11. The other case is going to be x plus 6 is equal to negative 2 root 11. Now, for the solutions, it's x is equal to, if I subtract 6 from both sides, it's going to be negative 6 plus 2 root 11. Let's make sure I make that a little neat. 2 root 11. And my other solution is x is equal to negative 6 minus 2 root 11. There they are. So be careful with those radicals. If they're not perfect squares, try to reduce them as much as possible. Once you reduce them as much as possible or make them into their most simplified form, a mixed radical, then you have your solution. Okay, let's move on to B. B is going to look like the following. I see 10m squared minus 40m plus 6. I see that they're actually both or all divisible by 2. Let's start by dividing everything by 2. And the reason is we want to reduce this as much as possible so that the numbers are a little bit easier for us. This is going to leave us with, instead of 10, it's going to be 5m squared minus 20m, and then plus 3 is equal to 0. The nice thing about equations is that rather than having to store that 2 out front, or I should say rather than equations, it's functions, in the functions unit, when we had a GCF or this greatest common factor that divided them all, we had to place it out front as 2 and bracket like this. But in this unit, if I have a 2 like this, because my right-hand side is equal to 0, or we're looking specifically for our x-intercepts, which are those roots or solutions, then when I divide a number away using the greatest common factor method, it actually just divides from both sides, cancels it, and reduces our numbers. Now, this is still symbolic of the same parabola or the same overall quadratic function, in this case, quadratic equation. Now what we're going to do is we're going to group our first two terms together. So I'm going to group these two, my 5m squared minus 20m. I'm going to remove out a common factor, which is 5, leaving me behind with m squared minus 4m plus 3 on the very outside because we don't touch that number. Now what we're going to do is our b divided by 2 method. So b divided by 2 all squared, which is equal to negative 4 over 2 all squared, which is equal to negative 2 squared, which is then equal to 4. We want to hold on to our negative 2 squared just so that we have it. This is going to give us the following. 5m squared minus 4m plus 4 minus 4 plus 3 on the outside because that constant term, we just left it. Now I want to remove this term outside. How do I do that? I must multiply it to the positive 5. So therefore, I can then place it out here in the constant spot. So this is going to be 5m squared minus 4m plus 4, close the bracket, minus 4 times 5 plus 3 is equal to 0. Because again, if I want to remove that negative 4 out, I must multiply it by the coefficient here so that it can be separated from the brackets. Now this is going to give us 5m squared minus 4m plus 4 bracket negative 20 plus 3. This is going to be equal to negative 17, which is equal to 0. Now what I want to do is convert this from a trinomial to its factored form. It's a perfect square trinomial. It's going to be m. We go up to our highlighted term, negative 2 all squared. Negative 17 is on the outside, which is equal to 0. Now what we're going to do is we're going to add the 17 to both sides. So we're going to go plus 17 plus 17. This is going to give us 5m minus 2 all squared is equal to 17. We must divide both sides by the coefficient term, so divide it by 5. And then this is going to give us m minus 2 all squared is equal to 17 over 5. We're going to square root both sides because we want to get it to our m being isolated. Now, what we're going to have to probably do is carry it off in this white space here, which we got more than enough room to do. So I'm just going to arrow up here. So in doing this, we're going to get our m minus 2. is equal to the plus minus root of 17 over 5. And then in this situation, 17 and 5, they're both prime numbers. We can't perfectly square root them, so it's plus minus of this radical. Therefore, our two solutions, and I'll just maybe vertically stack them, it's going to be m minus 2 is equal to the positive root of 17 over 5. Therefore, the answer for m is 2 plus the square root of 17 over 5. Our other answer, and maybe I should highlight them as we go. So there's our first solution. The second solution is m minus 2 is equal to the negative square root of 17 over 5. And then we're going to add the 2 across. This gives us m is equal to positive 2 minus the square root of 17 over 5. There we go. There's our second solution. Okay, now for some of you, you might actually wonder with this type of problem, we complete the square, we give ourselves the values here, 2 plus the square root of 17 over 5 or 2 minus the square root of 17 over 5. You can actually flip that order so it's the radical before the number that you add or subtract across. Either way, same answer, just be aware that it could be shown to you both ways. So what I mean by that is you could swap these two in terms of the 2 could be after the square root, or you could have them in the order presented. Either way is totally fine. All right, let's move on to example C here. Now, for example C, there's something that throws me off with this, and it's the following. We have a fraction mixed with some sort of integer values for our x and our constant. In order to get rid of the fraction, I mean, we could solve it with the fraction, but let's say we didn't want to. What we're going to do is we're just going to multiply everything by the denominator, and I'm going to actually include the negative with that. So we're going to multiply both sides by negative 3. And by doing so, what this is actually going to do is it's going to eliminate the fraction and only give us integer values. Okay, negative 3 times 3x, this is going to give us negative 6x. Negative 9 times negative 3 is positive 27, which is equal to, on the other side, we have negative 1/3 times 3, or negative 3. This actually gives us positive x squared. Now, what I'm going to do is to keep the positive x squared, I'm actually going to take both of these terms and bring them over to the other side. That's going to give us 0 is equal to x squared plus 6x minus 27 is all equal to that 0. Now what we want to do is complete the square from here. So we're going to group our first two terms together. This is 0 is equal to, we can't remove anything out of here, so we're actually just going to go right to our b divided by 2. B divided by 2 all squared is equal to, we have our 6 divided by 2, and this is squared. And then, oh, I want to double check a number here. I had a feeling something was off. Before we go into this, and before we go into this, let's just double check our trinomial. Negative 3 times 3 is negative 9. This should be a negative 9 here. This should be a positive 9. I kind of had a feeling something was off just based on those numbers. Now, always double check your numbers and be very careful with that before you start the problem. So we ended up getting negative 9 instead, which then is positive 9x on the other side. Now, this is going to be 9 divided by 2 squared. 9 divided by 2, which is equal to, I mean, we could make it a decimal, but I'm actually just not going to. I'm going to keep it as 9 over 2 squared. When I square both of them, I'm going to get 81 over 4. Okay, now we're going to substitute that in. So it's going to be 0 is equal to x squared plus 9x plus 81 over 4 minus 81 over 4. I'm going to have brackets around all that, minus 27. In order to remove that 81 over 4 out, I would have to multiply it by the coefficient here, but the coefficient here is just 1. So when I multiply those two things together, it's going to be 0 is equal to x squared plus 9x plus 81 over 4. We're going to close the bracket. We're going to bring out the 81 over 4 minus 27 on the outside. From here, we're going to go 0 is equal to, well, if I know that this is a perfect square trinomial, the factor is actually x plus the 9 over 2 that we got as the b divided by 2 value. And then negative 81 minus the 27, this is the same as negative 189 divided by 4, which is all equal to 0. And we already have the 0 on the other side, so we don't need that. Now what we're going to do is we're going to add that 189 to both sides. So let's just make sure we go plus 189 over 4 and plus 189 over 4. Now, this is going to give us the following. 189, and let's make sure I have in the black marker here, 189 over 4 is equal to x plus 9 over 2, all squared. Now what I'm going to do is square root both sides because we want to start by solving for x by the square root. This is going to give us the square root of 189, which in this case actually isn't a nice value. We can't really do anything with the square root of 189. We just kind of have to leave it as that. So our two answers are going to be the following. We're going to get the square root, and actually, you know what we can do with this is instead of 189, I can actually make this equal to the square root of 189. Let me backpedal that there. Square root of 189 divided by 2, because what's the square root of 4? It's just 2. So this is the equivalent form of that piece there. And again, this is going to be the plus minus version of this term. So now what we're going to go do is below is the two different terms here. It's going to be x plus 9 over 2. And for the 9 over 2, this is going to be equal to the positive 189 over 2. And then we also have the other term, which is x plus 9 over 2 is equal to the negative square root of 189 over 2. Now, this gives us two x values. When we subtract the 9 over 2 from both sides, we're going to get x is equal to, first of all, negative 9 over 2. And then let's actually make this, no, I'll keep them separate for now, and then we'll do an answer. So maybe I'll just put it a little more to this way. This is going to be x is equal to negative 9 over 2 plus the square root of 189 over 2. And here's where I was going with this. We can actually make this one fraction. Because they're both over 2, you can add and subtract terms with the common denominator. I'm going to make this negative 9 plus the square root of 189 all over 2. So that's our first answer, and let's make sure I highlight that piece here. The other answer is going to be the following. I'm going to take this as x is equal to the negative 9 over 2 minus the square root of 189 over 2. As a combined answer, this is going to give me the negative 9 minus the square root of 189 all over 2. There we go. So with these ones, if you can make them a common denominator and then blend them into one term, that will be ideal. In fact, that actually leads us into the idea of the quadratic equation, which we're going to see very shortly. Or the quadratic function, where we can take these things and put them into the equation, and then from the equation get specific values. But we'll talk about that very shortly. Okay, now let's go up to D. Do a very similar solution type here. First and foremost, we want to group our first two terms together. So I'm going to write this as bracket 4x squared minus 24x plus 47 on the outside, because we leave our constant outside. I divide both terms by 4. This is going to give me 4x squared minus 6x plus 47 is equal to 0. Now we can do our b divided by 2. b over 2 squared is equal to negative 6 over 2 all squared, which is equal to negative 3 squared, which is equal to positive 9. Now from here, let's just make sure we highlight that value of the b over 2, because we know it comes back up in our trinomial, or a perfect square trinomial. This is going to be equal to, we take this and go 4x squared minus 6x plus 9 minus 9, because we do a plus and minus of the squared case, plus 47 on the outside, which we haven't touched. Now, to move this negative 9 outside, we got to multiply it by the 4 out here. So when I do that, it's going to be 4x squared minus 6x plus 9, leaving that trinomial, minus 9 times 4, because we got to multiply it by the coefficient of the trinomial, or coefficient of this bracketed term, plus 47 is equal to 0. This is going to give me 4x squared minus 6x plus 9. And then on the outside, 9 times 4, we're going to get is negative 36. Negative 36 plus the 47, this gives us positive 11, which is equal to 0. Now what we want to do is just rewrite that trinomial as x. We know that our highlighted term was negative 3. X minus 3 squared plus 11 is equal to 0. I'm going to then start by subtracting my 11 from this, because this is technically our vertex equation. If I wanted to convert it from vertex to the specific x values, we want to move our constant term first, or move that q value. This is going to give us 4x minus 3 all squared is equal to negative 11. We're going to divide both sides by 4. So there we go. Negative 11 over 4 is our one side. It gives us x minus 3 all squared is equal to negative 11 over 4. Whoa, we should be looking for this right away. As soon as we go to square root this, look what's going to happen. We're going to end up getting a negative value under the radical, and this cannot happen. As soon as you see that the negative comes under this radical here, you're like, wait a minute, we can't do that. We can definitely have a plus minus of a radical, but we can't have a negative under the radical like this. And so right here, we would want to make the note. As soon as you see you square root a negative, just say cannot square root a negative, and I'll even write this in blue just to emphasize it. So cannot square the negative. And again, maybe in the future, you'll see when you introduce the complex numbers that you definitely can, but for now, we're going to say that there is no solution, or to really put it together, no real solution. And in lesson 4.4, we'll go on more about that, about real solutions, non-real solutions. We've talked about them before. Non-real solutions just mean it doesn't cross the x-axis, but technically it would be an imaginary number. So once we introduce that plane, it would have these solutions. But for this, it is a non-real solution, or there's no real solution to this question here. Okay, let's move forward into our next example. Example 5, solve by completing a square and then express your answers to the nearest hundredth. Okay, so this is one of those ones where now they're asking us to actually answer it in a very specific manner, or to a specific tenth or a specific decimal place. In this case, they say to the nearest hundredth. So just be looking for that. If they say exact values, keep the radical. If they say to a decimal place, you can answer a decimal place. Now, this one's very similar to one of those previous ones we just solved where we have fractions, and I don't really like fractions. So what I'm going to do is I'm going to rewrite this equation. I'm going to write the 1/4 x squared plus x is equal to negative 1/8. Now, in order to eliminate the overall fractions here, what we need to be thinking is, what is the lowest common multiple? Again, we could solve with the fractions, but I think it's going to be easier without it. So lowest common multiple, or the lowest common term that could multiply all of these and then cancel the fraction. Well, what is the first number that 4 and 8 both multiply to? They actually multiply to make 8. So we're going to go LCM is equal to 8, meaning let's multiply all the sides by 8. So I multiply this side by 8, I multiply this side by 8, and here's what you're going to notice. 8 times 1/4, or aka 8 divided by 4, that's 2x squared. 8 times x is equal to 8x. And on the other side, 8 over 8 is 1, and this is just going to be a negative 1 because the negative is going to stay. And hey, look, now our fraction is gone. So it's really important to be thinking, use the lowest common multiple to help you get rid of that denominator. This will come up back in rational expressions, which is one of our future units. So I just kind of want you to be thinking ahead to this. It also was in previous grades like Math 10C. You've probably seen this skill used before in order to eliminate these fractions. Okay, what I'm going to do now is to make this into its equation form, I'm going to add the 1 to both sides. So we're going to go plus 1 and plus 1 because I want to keep that x squared positive. It's going to be 2x squared plus 8x plus 1 is equal to 0. Now what we want to do is start completing the square at this point. To complete the square, we're going to group our first two terms. 2x squared plus 8x, close the bracket, plus 1 is equal to 0. I'm going to take out a 2 from both of these. It's going to be 2x squared plus 4x plus 1 is equal to 0. And when I say take out, I mean divide as a common factor. Now we're going to do our b divided by 2. b divided by 2 squared is equal to 4 divided by 2 all squared, which is equal to 2 squared, which is equal to 4. Now make sure you highlight that b divided by 2 term because we know it appears in the trinomial. This is going to make it 2x squared plus 4x plus 4 minus 4 because we do the positive then the negative, plus 1 on the outside is equal to 0. Now from here we're going to rewrite this as 2x squared plus 4x plus 4. I'm going to bring out this negative 4 by multiplying it to the 2 that's the coefficient of the bracket. So this is going to be negative 4 times 2 plus 1 is equal to 0. Now what I'm going to do is I'm going to carry this up over to the right-hand side here so we can continue forward. I'm going to rewrite this trinomial as the following. It's going to be 2, we add our x squared plus 4x plus 4 in the inside. On the outside, it was negative 4 times 2 is negative 8. Negative 8 plus 1 is negative 7. So I'm going to write negative 7 is equal to 0 like this. Now, I want to convert this from a trinomial to its perfect squared factored form, which is x plus 2 all squared minus 7 is equal to 0. Now, we have it in its vertex form. We need to add the 7 across or add our q value. This becomes 2x plus 2 all squared is equal to positive 7. We're going to divide by that coefficient term, divide by 2. When I divide by 2 to this, it's going to become x plus 2 all squared is equal to 7 divided by 2. Now we want to square root both sides. So once we have no coefficients and no sort of lingering terms, we can square root both sides. This gives me x plus 2 is equal to the plus minus square root of 7 over 2. Again, 7 and 2 are both prime numbers, so I can't square root either one of these. I can't simplify it any more than that. Now what I want to do is I want to type these into my calculator, but first let's just make sure we separate them into the solutions so that we can enter them properly. Okay, off to the side here, we're going to arrow up and do our one solution up here, and then we'll do our other solution right below it. The first solution is x plus 2 is equal to the positive root of 7 over 2. That means the x is going to be equal to negative 2 plus the square root of 7 over 2. And then to the nearest thousandth, or in this case to the nearest hundredth, which is the second decimal place, we're going to get an x value equal to 0.13. There we go. And we want to make sure we highlight that solution here. Perfect. Okay, now our second solution, which we're going to use as an arrow just right below that, we're going to get x plus 2 is equal to, instead of positive root 7 over 2, it's going to be negative 7 over 2 as a radical. This means we're going to have x is equal to negative 2 minus the square root of 7 over 2. And then as a value here, we're going to get that x is equal to, and I'll do that off to the side here, x is equal to negative 3.87. There we go. So that's our second root solution or x-intercept. Okay, perfect. So just be careful that when you're taking the square root, you do the positive and negative case, because a lot of you might just originally, when you first start doing these, be like, oh, that's good enough. I just square root it and then that's my one solution and we're good. No, it's always got to have the plus minus there. Okay, now going down below to our next example, example number 6, the length and width of a rectangle are 6 and 4 meters respectively. When the dimensions are increased by the same amount, the area of the new rectangle is 50 meters squared. Determine the dimensions of the new rectangle to the nearest tenth of a meter. Okay, and tenth obviously being one decimal place. Okay, let's start off with defining the couple things that were in this problem, because we want to be very careful with this. So they first of all tell us that they were like, the length and width of this rectangle are 6 and 4, and if they increase by the same amount, then it increases to this new 50 meters squared. Okay, first and foremost, part number 1, we know that area, or the area of the first one, was length times width, which was equal to 6 times 4, which is equal to 24 meters squared. That's what they're claiming, that the original area was 24 meters squared, by saying that they were originally 6 and 4. The second area, area 2, is equal to, we take the length plus some amount, which I'm going to call x, and we take the width plus some amount, which I'm going to call x, and supposedly if you multiply those together, you get 50 meters squared, which is our new area. And that x value is just simply the amount that we increase both by together. All right, now what we're going to do is we're just going to add our numbers into here. So our length was equal to 6 plus x. Our width was equal to 4 plus x with that new section, which is equal to the 50 meters squared. Now what we want to do is expand this and then solve it just as we've done before. So let's expand this bracketed terms here, or the 6x, or 6 plus x, 4 plus x. This is going to give us the following. When we continue this down, and I'm going to make this actually step number 2, is us actually starting the algebraic process here. 6 times 4 is equal to 24. We then go 6 times x is plus 6x, 4 times x is plus 4x, and then x times x is x squared. This was all equal to the 50 that was on the other side, which is the area that we are looking for of this new rectangle. Now, I want to keep the x squared positive, so I'm actually going to subtract the 50 from both sides, bringing it over to the left, and I'm going to rewrite this in terms of the quadratic equation in descending order. X squared plus 6 plus 4 is 10x, and then 24 minus 50, that's going to give us negative 26. This is all equal to 0 once we've brought it across. Now we're going to group our first two terms. So we're going to go x squared plus 10x, close the bracket, minus our constant is equal to 0. We can then go into our b over 2 squared, which is equal to 10 divided by 2 all squared, which is equal to 5 squared, which is equal to 25. Again, always highlight or circle or box that b divided by 2. Now from here, we're going to write this as x squared plus 10x plus the 25 minus the 25, close the bracket, minus 26 is equal to 0. If I want to remove out this negative 25, I must multiply it by the coefficient here. Fortunately for us, it's 1. So this is going to become x squared plus 10x plus 25, close the bracket, minus 25 minus 26 is equal to 0. That's going to leave us with x squared plus 10x plus 25, close the bracket, negative 25 and negative 26, when they come together, you're going to get negative 51, which is all equal to 0. Now I'm just going to convert this instead of the trinomial. It's going to be x plus 5 all squared minus 51 is equal to 0. Now this is our vertex form. We recognize this from our quadratic functions unit when we converted from our regular trinomials, our in general form, to vertex. This is how it appeared. Now what we want to do is solve for our specific x's. Again, how did I get that plus 5 in here? Came from our b divided by 2. So just connect those two things together, that those happen in the same way, or that they carry the same sign and that they are the same value. And then what we're going to do from here is we're going to isolate for the x. So let's continue that up above here. When we isolate for the x, first and foremost, on our one side, we have x plus 5 all squared minus 51 is equal to 0. I'm going to add 51 to both sides in order to get rid of it from the left. This leaves me with x plus 5 squared is equal to 51. Now what I'm going to do is square root both sides, square root here, square root here. This is going to give me x plus 5 is equal to the plus minus square root of 51. Unfortunately, it's not a perfect square, but that's exactly why they're asking us to round it to the nearest tenth of a meter. Now we're going to separate it into the two following cases. We get x plus 5 is equal to the square root of 51. And then in our second case, we're going to get x plus 5 is equal to the negative square root of 51. All right, solving for the x values, we're going to subtract 5 from both sides, and we actually do this for both equations, which is really nice. The only thing that changes when we do our different cases is the plus and minus on the radical. This is going to give us x is equal to negative 5 plus the square root of 51. And our other x value, it's going to be x is equal to negative square root of 51. Let's make sure I got that all in there, and the negative on the outside, so negative square root of 51 minus 5. And this is going to give us the following. X is equal to, for the first case, it's 2.14. For the second case, it's going to be x is equal to negative 12.14. Now, here's what I want you thinking about this. When we think about what these x values represented, let's just zoom out for a half a second here. I go down and I look at it and I see, oh, well, the x values were how much both of these increased by, in terms of if I add a strip to the length and I add a strip to the width, it gave me this new 50 meters squared. We can't add a negative value. This is what we're going to call extraneous in this unit. It means it does not apply to the actual solution to this problem. So I'm just going to make that just a touch neater, and we're going to put a line through it, and we're going to write ext. It's really important you cross it out and you say that it is not considered in the solution, because if I took that 6 and I subtracted 12, I'm in the negatives for my length. And if I took the 4 for my width and subtracted 12, I'm in the negative for my widths. That means I'm losing some sort of length and width in terms of a negative value. It just doesn't make sense for this problem. Whereas we can definitely add a certain amount of length and width, in this case, the 2.14 to both. So this is what we're going to add. Therefore, in our solution, we need to be very clear with the following. They asked us what this new length and width were to the nearest tenth. Therefore, the length was equal to this, or I should say the new length was length plus the x value, which is equal to the original 6 plus 2.14. This means we're going to get a value of 8.1 meters for the length. And then my width plus x to get my new width was 4 plus 2.14, which is equal to 6.1 meters to the nearest tenth. There's the solutions you're looking for in terms of the new length and new width that allow us to obtain that specific 50 meters squared that was the new area. Now, let's just make a note about this, because we talked about that extraneous value, meaning that it doesn't apply to this specific situation. By their definition in the bubble here, an extraneous root, or the extraneous solution, is a number that is obtained in solving this equation which does not satisfy the initial restrictions. That's the important thing to be thinking about. Does it satisfy, or does it fit the narrative, or does it fit your solution given the overall context or given the overall situation? Because theoretically, yes, this is the x value that applies to this equation. We solved for it, we found it, but does it actually satisfy the original? No. And in fact, we could actually do this if they ever said algebraically verify. you would take that 12 that's down here, plug it in for the x's both here, and just think about this logically. 6 minus 12, 4 minus 12, yes, it might satisfy it in terms of it might go into the brackets there and then potentially give you that solution, but we also want to be thinking about it's going to give you the negative negative, which is positive. Is it going to satisfy it in terms of like the actuality of the problem? Sure, it might give you that 50 that you're looking for. It might steer you back right to this 50 meters squared, but in actuality, a negative value here for a length and a negative value here for a width is not going to satisfy an area because we can't have negatives in real life. There's no such thing as going back on a measurement unless we're talking about it being like left or right in orientation, which is more of like a physics problem at that point. So keep it simple and be like, if it does not satisfy the initial restrictions on the variable, meaning it has to fit the context of the problem, then we're going to say cross it out and write extraneous because it does not fit those restrictions. All right, here's where you want to go on to your assignment, which is your textbook problems. Please get work with these because completing the square, you might need that refresher because it's been a while since we've talked about it in quadratic functions. So please go through this because you will want to master this skill. It is the second algebraic type. So first algebraic type was factoring, which we learned in 4.2. In 4.3, we learned completing the square, which is our second one. In lesson 4.4, which is coming next, we're going to learn our final algebraic type in order to solve for solutions, x-intercepts, or roots, and that's dealing with the quadratic equation. All right, good luck with your practice.